All right, so last time we talked about what a buffer solution is, and this time we're going to talk about buffering action. How is it possible that adding, say, an acid or adding a base to a buffer solution doesn't cause the pH to change by much? And in fact, when you add a certain amount of acid or a certain amount of base, how much does the pH change by? So we'll be able to learn that as well. So again, it says a buffer is able to neutralize either an acid or base that is added to it. We'll talk about how that happens. Very, very, very important. Uh, Resulting in only very slight changes in pH. So it's not like the buffer completely resists changes in pH. It just doesn't change by as much as if you, say, added an acid or base to water. For example, take a look at table 19.3 on page 750. So suppose you have 1 liter of a buffer solution versus 1 liter of water, I suppose. So this buffer solution consists of 0.1 molar sodium acetate and 0.1 molar acetic acid. So that's our first one here. Actually, let's look at the pure water, the data for the pure water first. So when you add 0.010 moles of NaOH to pure water, the pH goes up by 5. So it goes from 7 to 12. So this is a decrease in the H plus concentration of 10 to the 5th. Remember, pH is a logarithmic scale. So the hydrogen ion concentration goes down by a factor of 100,000. So what if we add 0.010 moles of HCl to a liter of water? pH is going to decrease by 5. So it's going to start at 7, neutral, and it's going to go down to 2. This results in an increase in the H plus concentration of 100,000, 10 to the 5th again. Think about that, 0.010 moles. That's all we're adding. And the pH changes by a huge amount. Let's look then at what happens if we add either acid or base to a 0.10 molar solution of acetic acid. So instead of pure water, so we're adding it to acetic acid. If you add 0.010 moles of NaOH, a base, to a 0.1 molar solution of acetic acid, the pH goes up. Again, I didn't mention this before, but you're adding a base. So of course, anytime you add a base, the pH will increase. And the pH this time is going to go up by a little less than 1. How does this factor into the concentration of H plus? So H plus concentration will decrease by a little less than 10 times. So this 8 times, remember 1 on the pH scale corresponds to 10 times the difference in acidity or H plus concentration. So H plus is going to decrease by about 8. Now let's say you add 0.010 molar HCl to our acetic acid solution. Of course, adding an acid is going to cause the pH to decrease. So pH goes down by 0.89, and this results in an increase in the H plus concentration of a little less than 8. Now, let's look at our buffer solution. So again, here is our buffer. 0.1 molar sodium acetate, so acetates here being the conjugate base of our weak acid, acetic acid. So if you add 0.010 moles of base to this buffer solution, the pH goes up by 0.08. Not a lot at all. This involves a decrease in the concentration of H plus by a little more than 1. A little more than a factor of 1, 1.2. Quite the difference between adding the base to this solution versus adding it to pure water, or even to the solution of acid by itself. Look at that. Goes from increasing by 0.91 to increasing by not even 0.1. Likewise, adding 0.01 moles of acid to our buffer, the pH is going to go down by 0.08. and an increase in the hydrogen ion concentration by a factor of 1.2. So again, the point being that for a buffer solution, you add acid or add base to that solution, the pH will either increase or decrease, depending on what you're adding to it, by a very small amount. Why? Why does this happen? What is going on with that solution that allows it to really withstand huge changes in pH, huge changes in acidity? Well, let's take a look at an example and see how this works. So go to 19.4 on page 749. It says, if we add 0.010 moles of solid NaOH to 1 liter of a buffer solution that is 0.1 molar in acetic acid and 0.1 molar in sodium acetate, how much will the H plus concentration and pH change? Assume there's no volume change due to the addition of the solid NaOH. So we just have 1 liter solution. So let's do this. Let's start off with our ionization equation for our weak acid, acetic acid. So always want to start with this. I'm not going to put water in this time, but you can put water in. Okay. Now this is a buffer solution. So this solution contains both unionized acetic acid and acetate. So we have 0.1 moles per liter. This is in a liter of solution. So we have 0.100 moles of this, and we have 0.100 moles of this. How much H plus is in this solution? An extremely small amount of H plus is in the solution. All right, so here's the deal. You have a buffer solution. You add an acid or you add a base to it. What is that added acid going to react with? Or what is that added base going to react with? Well, if you add an acid to a buffer solution, it reacts with the basic component of that buffer. That would be here, in this case, the acetate ion. If you add a base, it's going to react with the acid. Now be careful, the NaOH doesn't react with H+. There's a really, really, really small amount of it in there. And so the added base, in this case NaOH, is going to react with the acetic acid. So make sure, first and foremost, you understand and know and recognize what's the reaction is going to occur between. When you add sodium hydroxide, what exactly in that buffer solution does it react with? All right, so let's set that up. Let's write an equation. We always want to write the equation for the reaction that is occurring. So we have acetic acid plus, and you have two choices here. You can write NaOH, or you can just write OH minus. So the book writes NaOH. I think I'm going to write just OH minus, just to show you something a little different. Now, what goes here? Does this reaction go to completion, or do we have equilibrium situation? Technically, this reaction goes to completion. At least this part of the reaction does. So what do you make when acetic acid and hydroxide react? Well, you get acetate, more acetate. I think there was already some in the solution to begin with, and water. All right, so here's the thing. We're going to set up, yeah, you've been waiting for it. So we've been talking about it, but here's when we really need it. So we'll really use a SCAR table. It'll be really helpful with buffering action. When you add an acid or you add a base to a buffer solution. All right, so how much acetic acid do we start off with? Now, first of all, we talked about this before. In your SCAR table, use moles, not molarity, not pressures like we can with ice tables. Use moles, has to be moles. All right, so we start off with, what was it, 0.100, and I'm going to write it this time just so you know that this is moles. 0.100 moles. To that, you add, according to the problem, 0.010 moles of sodium hydroxide. and you have already in the solution, because this is a buffer, you already have 0.100 moles of acetate. Again, this is from, I don't know how I want to show this here, from the sodium acetate that was used to make the buffer solution. And then water, we don't care about. All right, notice anything here about the quantities? So at this point during the reaction, the hydroxide is the limiting reactant. How much of the limiting reactant reacts? That's right, all of it. So how much acetic acid reacts? 0.010 moles. And how much more acetate is produced? 0.010 moles. All right, so that means after the acetic acid has reacted with the sodium hydroxide, how much acetic acid still remains in the solution? We have 0.090, again, that's moles. We have none of this, of course, and we have 0.110 moles of acetate. Now look at what we have in solution. What exactly is in this solution after the reaction with the added base? You have acetic acid and acetate. You have a weak acid along with its conjugate base. You started off with a buffer solution after the addition of the sodium hydroxide. You still have a buffer. You still have a solution that contains lots of a weak acid and its conjugate base. Now, what were we asked to find originally? We're asked to find the H plus concentration and the pH of this solution. I think we've talked about this before. There's two ways of doing this. Anytime you have a buffer solution, you can use the Ka, or you can use Henderson-Hasselbalch. So I'm going to use Henderson-Hasselbalch. The book uses Ka. This is good. This gives you options. So let's use Henderson-Hasselbalch. We'll have to do a little bit of manipulation because this is going to give us the pH. So recall that the pKa of acetic acid is 4.74. Remember, negative log of 1.8 times 10 to the negative fifth, plus the log of what goes on top? Conjugate base or acid? What goes on the top, even if it's a POH, Henderson-Hasselbalch? Conjugate or the acid or base? Conjugate goes on top. So now, interesting here, a couple things. One is that we have moles in our SCAR table, and we want to plug into our Henderson-Hasselbalch concentrations. Except, a couple things here. One is that the volume of the solution is 1 liter, so those moles are also molarities. Secondly, since you're dividing them here, the liters, since we're in the same solution, those volumes are going to cancel. So you can just put moles there as well. So I'm going to put molarity just so you're not extra confused. And why don't you pause the video and try it out? See what you get for the pH. Pause now. So my calculator gives me a value of 4.83. Now, again, how much did the pH go up by? Not a lot. So we could have calculated, actually we did, it's shown in the solution. What was the pH before the addition of the base? So you have equal concentration of the acid and its conjugate base. And so the pH of this buffer solution before adding the base is 4.74. So how much did the pH go up by? It went up by 0.08. That is it. Not a lot. What if you added hydrogen chloride gas to this buffer? What would it react with? Well, hydrogen chloride, hydrochloric acid, is going to react with the basic component of the solution. It would react with the acetate. So we'd want to write the equation for the reaction between acetate and H+. And then our approach to finding the pH or H+ concentration would be similar. By the way, to find the H+ concentration, we can anti-log negative 4.83, and that will give us our value. All right, your turn. Number 25 on 765, except I'm going to change it up. I think there's a typo there. Let's take a look. It says find the pH of a solution that is 0.22 molar in nitrous acid and 0.15 molar in sodium nitrite. So it wants you to find the pH of that buffer solution, just like we talked about in the last lesson. Next, letter B, find the pH after, let's change that. It says 0.25 moles. Let's do, we're going to do 2. So number 1 is find pH of the buffer solution. Number 2, let's find pH after adding 0.050 moles NaOH. So don't use the value that's in the book, use 0.050 moles. And let's add one. Find the pH after adding 0.050 moles of HCl. And again, each time we'll assume that there's no change to the volume of the solution. It says 1 liter. We'll assume it stays 1 liter. All right, let's go ahead and pause the video and set those 3 calculations up. First, calculate the pH of the original buffer solution. Next, calculate the pH after adding 0.050 moles of NaOH. And then calculate the pH after adding 0.050 moles of HCl. Go ahead and do that now, please. All right, so here's our setup. We have concentration of the conjugate base nitrite NO2 minus 0.15 molar. Concentration of the nitrous acid 0.22, so I just use the Henderson-Hasselbalch equation. I could use Ka. You know everything except for the H plus concentration. So if you're using Ka, you would find H plus, take the negative log of that, and you get your pH. So pH of the original buffer solution, 3.18. Next, what is the pH after you add 0.050 moles of sodium hydroxide? So I set up my SCAR table. So of course, the sodium hydroxide is the limiting reactant. And so still going to have some nitrous acid remaining in the solution, still going to have some nitrite ion in solution, so still a buffer. So once again, I'm going to use a Henderson-Hasselbalch. Make sure to put concentration of the conjugate base on top, acid on the bottom. The negative log of 4.5 times 10 to the negative 4th is 3.35, so I just put that value in here, and we get 3.41. So the pH went up by a little bit, quite a bit. Again, though, not super significantly. Next, maybe I wasn't clear on this, hopefully you understood. That is start over, take that same buffer solution into it, instead of adding 0.050 moles of NaOH, you can add 0.050 moles of HCl. So very important, the acid is going to react with the base component of your buffer, which is the nitrite ion. So we write that equation for that reaction, set up our SCAR table. Still have some nitrite in solution, still have some nitrous acid. This is still a buffer solution. So again, Ka or Henderson-Hasselbalch. Be careful though. So again, on top always goes the conjugate base, which is not on the right side this time, it's on the left side. So 0.10 molar is the concentration of nitrite in that resulting solution. 0.27 is the concentration of the nitrous acid, and we end up lowering the pH a little bit, 2.92. All right, a lot going on here. We'll do some more calculations similar to this later on, where we're looking at amounts of substances that remain in a solution after adding so much acid or base to your original solution. All right, that concludes this lesson. Next time we'll talk about how to make a buffer. So how exactly do you make a buffer solution? There's actually a couple different ways, and I will teach you both of those. All right, thanks for watching.